I've planned 3 theory lectures today, and they will be hopefully comprehensive enough to understand, let's say, diffusion MRI to a level where you should be able to then continue in the afternoon with the practical session. So the practical session will be with a software tool called Explore DTI. If you haven't got the software yet, feel free to send me an email, and then I'll reply with the links that you need to download the software. I'll already give you a bit of a heads up. So I've got pre-compiled standalone versions of Explore DTI. That requires you to install the MATLAB runtime libraries first for your operating system. And then you can use this main Explore DTI app or exe file after you've installed those libraries. So the good news is you don't need any, everything's free, you don't need to pay for anything. If you do have MATLAB, you like the software tool MATLAB with the required toolboxes, then you can also opt to use what I call the MATLAB native version, which runs in MATLAB itself. So you don't need to install anything then in addition to that. I'm getting a lot of Zooms and everything, so I'm going to check whether... Okay, send my email address. Somebody already did that. Great. Okay. All right. So the reason I'm starting to talk about this now is that it may take a while to download. Especially my experience with downloading stuff in Iran can be slow. So, I'm giving you enough time now to download this tool and install the tool. I actually this morning replied to someone who requested Explore DTI. Maybe that person, if he or she is in the audience, could forward it to the organizer, and then the organizer could send all the links to everybody else. So, that already saves me some time to reply to everybody. But I'm happy to do so. So you can do that. You can send me an email, and in between my lectures, I'll reply then. You can do that too. All right. Anything else? Anything else practical? And what I'll do then, in a few hours, is I'll send through. I can also. I can do that. 1 second. Okay, what I'm going to do now quickly is just throw everything in the chat, obviously, and then that solves everything. Okay, so this is kind of the default reply that I sent to everybody requesting the software. There you go. So you should see in the chat all the links. So there's standalone versions. So there's 3 links there for the Mac, the Windows, and the Linux. But first, install this runtime compiler. So you go to your own operating system, situation. You download the relevant runtime libraries first. But if you have MATLAB with the required toolboxes, they're also indicated there, like image processing, statistics, curve fitting, optimization toolboxes. Then just use the MATLAB version. There's also a manual. To be honest, it's a bit, it hasn't been updated for a while, which is typical with manuals, but, And there's also a Google forum where you can ask questions, etc. And, for updates and everything, you could also follow the Twitter account. Okay, so sorry for that little intermezzo, but, let's see. Okay, back on track. Okay, I'm not sure why screen is flickering, so I'm gonna. Okay. Okay. All right. I guess you can see my screen again. So let's continue. So the Explore GI, so that's going to be kind of a hands-on. I think for practical reasons, I'll be doing kind of a demo exercise thingies, and then you can try to replicate it. So I'll give you some time, and then we can discuss this. And so what this tool basically does is that given a diffusion MRI dataset, and I will send you, again, a link in a few hours or so to some tutorial data, and then you can play around with it, see how Explore TI crashes, stuff like that. And we'll take it from there. All right, so let's move on. Okay, so first lecture, I will be introducing many key concepts, and I'll be quick, yet I will start from scratch. And I'll literally start with an MRI 101 course. There's 7 Nobel Prizes in this area. And this is a field which is always expanding. And the more you learn about it, the more you realize it's more complicated than you think it is, like with everything almost. But I'll go through some of the real basics, okay? But I'll do this quickly because the focus is on, diffusion tensor imaging. But diffusion tensor imaging literally is diffusion tensor MRI. So then you need to know a bit about MRI, okay? So, all right. So let's consider this, brain. Well, we've got all these little cubes, voxels. But within a voxel, within a human tissue, we've got molecules, many molecules, and it's the spinning charged particle, hydrogen atom, that is important. It acts like a little magnet field, if you want. And this spin, think of it like a little magnet bar. Okay. All these spins, these proton spins, they're basically oriented randomly, causing the net magnetization to be 0. Okay. This is in any tissue where you got all these spinning protons. And there's many, right? It's like the number of Avogadro, so like 10 to the 24. There's a lot of them. Okay? In MRI, you're aware we're looking at a very big magnetic field, a big magnet. Why is this important? Well, if we now put a subject into the scanner, then thinking again of this voxel, all these little bar magnets, they will be now aligned along this main magnetic field. Okay, and you'll notice that the low energy spins, I'm getting a notification here again. Let's see what's going on. Oh, okay. What's going on here? Are you still there? Jesus, I think
we can hear you.
Okay. This is weird. I can't see the Teams meeting here again. Let's see. Sorry, guys. Bear with me. Bum, bum.
It should just minimize by the side of your screen if you don't use it for some seconds.
No, I also have somebody waiting in the lobby. Okay. All right, sorry about that. So you can still see my presentation?
Yes.
All right. Mm-hmm. Okay, so sorry again for the hiccup. We'll continue. So like I mentioned, there's more spins with spin up, like low energy, than the high energy, causing the existence of a net magnetization. All right. So if you think of it, if your body enters this magnet, it becomes a little magnet of its own. Right? So you get magnetized. Also, another thing that happens is all those little spinning protons, they start precessing. They start orbiting along the main magnetic field. And it's called precession. And the frequency at which they are precessing is called the Larmor frequency. And you can think of it as the same physical principle in a way that if you have a spinning top in the gravitational field, I mean, as a kid, hopefully you also played with spinning tops like I did, and you just give it a good spin. You'll see it really rotates quickly around its own axis, but at the same time it wobbles around, right? And so the same happens with these little magnets. They start precessing around the main magnetic field. And so what happens in practice then? Okay, so you're in the scanner. You're lying in your big magnet. Your body becomes magnetized. So the M0 is different from 0. So you're magnetized. If you then submit frequency, radio frequency, with the Larmor frequency, with exactly that rate, then what happens is that you've got switches in energy state, causing your net magnetization. Oh, there's somebody in the lobby again. Let me quickly admit. All right. So now we've got 50 people in the meeting here. Okay, that's fine. All right, we'll continue. So what happens then is that basically what happens is that the low energy states, they basically get flipped, and this causes your total magnetization to become 0. But the cool thing is, if you then stop sending in these RF frequency, electromagnetic radiation, then your body basically starts to emit radio frequency, and your somebody else. By the way, is there some thing I can do where people get automatically bumped into my meeting? It's something I should check. Okay. More and more people. The more the merrier. All right. Okay. Anyways. I should really check whether down. Okay. Sorry about that again. So where was I? Okay. So your body basically emits radio frequency, causing your net magnetization to ramp up again, right? So what basically happens is there's relaxation processes going on. This is called longitudinal relaxation. Then something else happens. Because of the precessing, your normal component of your relaxation is 0. Okay. If you then send in that frequency, because they were all precessing randomly, now because of the resonance aspect, all these precessing spins, they're now kind of rotating in the same way, and that causes your net magnetization, the transversal magnetization, to become non-zero. And then if you wait again, they get emitted, and they will all be relaxing back in such a way that the transverse magnetization is 0. I know this is a bit a long-winded way of explaining all this, but the point I want to make is, to put it simply, when your body goes into the scanner, it becomes magnetized. If you send in a radio frequency, then the longitudinal magnetization becomes 0, and the transverse relaxation becomes non-zero. And if you then wait, then relaxation processes occur and your body basically sends out those frequency information. When I'm explaining it like this, I know it's kind of a simplified version, and people are then typically afraid, like, oh my God, I'm getting radiation. But it's all, as far as we know, it's completely safe. Nothing to worry about, right? It's the same principle in a way like a microwave, where you have resonance of your molecules, but you're not getting cooked unless it's a really, really big magnet and high frequency components. So take home message: 2 types of relaxation: longitudinal, transverse. And then obviously, we wouldn't be physicists or mathematicians if we didn't show any graphs. So this is how longitudinal magnetization looks like. It's an exponential. This is the formula, which you can derive from the block equations. And this is, spin lattice relaxation, longitudinal relaxation. And as you can see, it ramps up with time and then plateaus. And then transverse magnetization, kind of the opposite.
The slides are freezed.
The slides are frozen. Okay, what I'll do is I'll share them again. Let's see what happens. Can you see them again? Okay, so I don't know if you can see this, but like there will be an animation going on. I don't know if you see this. Exactly. Okay. And then you should also see the transverse relaxation. All right. Okay. So yes, and this is so the transverse relaxation is called spin relaxation. This is a quick table overview that different tissues have different relaxation properties. So the curves that I showed, they're different for different tissue types. And this is because of, susceptibility. Basically, different tissue types have different components, different, let's say, densities of these spinning protons, and hence their relaxation properties will be different. Okay? So if we were to look at white matter, gray matter, and CSF, you would see different relaxation curves. And it's the signal, which is basically the signal is basically originates from the relaxation properties, and so the contrast is basically caused by the difference in the relaxation profiles. Okay, and so when we look at an image, then the differences to the image contrast that we get is due to the different relaxation properties of the different tissues. And here you see an example of a T1 weighted and a T2 weighted image. Okay, so I hope this 10-minute explanation of MRI kind of sinks in. So we will be looking at relaxation properties, induced relaxation properties, I should say. And the cool thing is, obviously, well, we don't have to cut open the person's brain to look into the brain. All right. And MRI is more than only the brain, but obviously, in this NeuroTRACT association, I think we'll focus mostly on the brain here. All right. So a bit of context. Well, we can investigate the brain in many, many ways, and obviously, MRI is one of the many neuroimaging techniques within the field of neuroscience that you can use to investigate brain properties. But even if you focus on MRI, there's many techniques within MRI: functional MRI, structural MRI, perfusion MRI. There's angiography, looking at blood flow. spectroscopy, looking at metabolites, and all these things. Yeah, the way I see this, it's like MRI is like a piano, right? I mean, it makes music, but you can choose which type of music you want to play on it, right? It's the same with all these different sequences, image acquisition sequences that you can use then to get information of the tissue that you're imaging. All right. So now we're approaching diffusion imaging in short, right? So diffusion MRI, diffusion tensor MRI is something we'll come back to in a moment. But you have to keep in mind that diffusion tensor MRI is already like a step further. If you're talking about diffusion MRI, you would be looking more at diffusion weighted imaging. This is kind of where it originated. And I always make the joke, we don't call it diffusion imaging anymore. Sometimes we call it confusion imaging because it's so complicated, especially with kind of a medical arena. And something I asked, I kind of forgot to ask all of you is what is your backgrounds? So maybe it's probably most efficient just chat what your background is like. Are you a mathematician? I mean, some of you are obviously students, so you're not a physicist yet or a doctor yet, but it would be good to have kind of quick overview. So I see a lot of people chatting now. It's great. Okay, so mostly medical students. Great. Some neuroscience students. There's a few physicists. It's always good to see some physicists. I'm a physicist myself as well, but nobody's perfect, so that's fine. All right, medicine, psychology, clinical psychology, cognitive neuroscience, radiology. Okay, good. Well, I was hoping for such a diverse background because even veterinary. Okay, nice. Okay, because this is a type of lecture that I'm now giving. I hope the things that I'm saying kind of stick to everybody. By the way, I see 2 hands raised. Is that on? Is there something somebody wants to say? So I think Masha raised her hand. But okay, no worries. Well, you can always lower your hand then. Yeah, okay, great. Okay. So yeah, I've got a good idea of the background of all of you, so that's nice. I'll go back to my lecture now. So indeed, confusion imaging, again, this is something I noticed, especially with people with a less technical background, that it can be difficult to understand this field. So what I'll do now is I'll continue with what is diffusion MRI. All right. So obviously, when you want to know what diffusion MRI is, then you need to know what is diffusion. And diffusion is I think the simplest explanation is like with this glass of water and a drop of wine. So if I put a drop of wine, well, or a drop of ink, depends on your preference. If you drop that into the glass and you wait long enough, you'll get the same kind of hue on in your glass, right? So all these molecules, they spread around. If I put this in an animation, you can look at it like this. Okay, so let's assume all the green particles on the left are water molecules and all the red particles are wine molecules. And if I remove the barrier, I hope this animation shows with you as well. So if I remove the barrier, then you can see all these particles like intermingling. And this is because of every particle has kinetic energy. It moves around. Thermal energy. So thermal energy is basically molecules moving. And if they move at a higher rate, they've got more energy. And this little motion of molecules, this erratic motion, is also called Brownian motion because it was first described by Robert Brown. As you can see, this guy was very excited with his discovery there. Happy chap, right? And so this is what we call Brownian motion. Okay, and so this spread of molecules at the microscopic level mounts up to diffusion, which is a macroscopic effect in a way. Okay, so we will be looking at a kind of a flux of one substance to the other. Obviously, I was talking about a drop of wine in a glass of water, but the same principle holds for a drop of water in a glass of water. You don't see it, but it is going on. So it's called self-diffusion. So water molecules in a glass of water, they are also moving around. It's not static, right? I mean, overall, there's a fluid, and there might be some convection going on, like big chunks of part of the water in a glass moving around slowly. But at the microscopic level, at the little element, you'll see all these molecules really quickly moving around in an erratic way, and then they kind of spread as a global effect. Okay, two types of diffusion that I quickly want to address. Isotropic okay, you may also get this kind of shriek going on. I was actually startled myself. I forgot I put it in there. Some more people into the meeting. All right. Okay. Oh, they're gone. Okay. So this is a reaction I get from many people as well. It's like, oh my God, what is anisotropic diffusion? This is a difficult word. Well, don't worry about it. I'll explain in a moment. So first, isotropic diffusion. So if I start the animation again with the particles in the middle, then you can appreciate now that the spread of these red molecules is the same in each orientation, right? So going up, going down, left, right, the spread of the red particles is the same. This is what we call isotropic diffusion. And in 2 dimensions, you can visualize this kind of probability of spread with a circle, and in 3 dimensions with a sphere, right? It's kind of, so you have to think of the surface of the sphere to be like an isoprobability function that grows in time. And this kind of gives you an idea of the spread of these molecules. Anisotropic diffusion, by contrast, is the opposite, meaning there is a preferred orientation. And let's assume that we have, in this case, in this example, some barriers that are horizontally aligned. So they're going left, right. It's not hard to imagine that if you have molecules now, if you were to allow them to move, then let me run the animation, that these, okay, so I'm going to add some more people to the lobby. Okay, great. If you then allow these molecules to move around, they will be more hindered going up, down because of these barriers than left, right. Right? You think of it like highways, right? If you're driving your car, it's going to be a lot more difficult to go left, right than going, front, back along the autobahn, right, to the highway. So this is what we call anisotropic diffusion. There's a preferred orientation in which the molecules are spreading because they're probing their environment and they're bumping into each other, but they'll be bumping more against these barriers, so they have difficulty crossing them, but it will be easier for them to go along the highways. And then again, schematically, you can kind of visualize or characterize this spread of molecules in 2 dimensions with an ellipse, and in 3 dimensions, you can visualize this with an ellipsoid. This is the most straightforward 3-dimensional representation of molecules spreading. Okay, another aspect, hindered versus restricted diffusion. Okay, I'm going to show a similar animation again. Actually, it's kind of the same one as before. This is an example where I have some barrier, and let's assume this barrier is semi-permeable, meaning that it will be hindering the molecules. And I'm going to start the animation so you can appreciate these red molecules. They will be going more left, right than up, down. The green ones, they've got easier way. It feels like they're not hindered by anything. So they just move isotropically. But the red ones, they're hindered. But they can still cross the barriers. Okay. Restricted diffusion, on the other hand, if I now start the animation, these red particles, they will stay within those boundaries that I'm showing you here. So restricted diffusion means that you'll typically see anisotropic diffusion, like with the red particles that you can see now, but they will not be able to cross the barriers. So it's highly anisotropic. Think of it like that. Well, in this case at least, right? If you think of these barriers being a cell, like let's say a little sphere, then obviously within this cell, you could argue, well, the diffusion is isotropic because they will be going, in any direction at the same rate, but then they will hit the barriers and they will not continue. So in a way, restricted diffusion versus hindered diffusion are different concepts than isotropic and anisotropic diffusion. I hope that makes sense. And the good news is, it wouldn't be fun if we couldn't put a formula to that. There was a very smart guy called Einstein who came up with this equation, the diffusion equation, which basically says that in this free diffusion environment, the spread of these molecules, the average square displacement of these molecules is proportional with time. So the longer you wait, the more that these particles will have spread. Anyway, it's obvious. But the way to characterize this is given by this elegant equation. So yeah, really cool, because now we can quantify this, and it means we can also predict things like if we know how much time it took to spread, and we knew how far they spread out, we can compute this. For instance, we can estimate this diffusion coefficient D, and D depends on temperature, viscosity, some other properties. And then so the cool thing is that this diffusion process, it's kind of described in a way. You can put a formula to that. And as a physicist, we love formulas, obviously, but it gives us a hold to compute things, to predict things. And this is going to be important later on. Okay. And like I mentioned before, this drop of wine in a glass of water, you can think of it also, it also works for a drop of water within a glass of water. So we call it cell diffusion. And as most of you know, the brain contains a lot of water molecules. Well, our body in a way. And isn't something like 70 or 80% of all molecules in our body are water molecules? Isn't that like the joke they make, like, 80% of our body corresponds to a cucumber or something like that? We've got 80% in common with a cucumber because of the water content or something like that. Anyway, point I want to make is our brain or tissue, any tissue in our body, there's a lot of water molecules in there. And they are also moving around. We've got water molecules that are bombarding in tissue, moving around, because again, we're looking at erratic motion of molecules, and our molecules are moving around. And obviously, some molecules are not water molecules, but they do have spinning protons. And it's all about spinning protons, right? So the cool thing is, conceptually, we could also look at diffusion in brain tissue, right? And how would that work in brain tissue? Well, in brain tissue, as the image shows here, it's kind of a Klinger, dissection. We mostly have fibrous tissue in our brains, meaning that there are like coherent highways. It's kind of sketched over here. And it's not hard to imagine that within the brain, we also have anisotropic diffusion. It could be hindered, could be restricted diffusion, but there's clear architecture that guides the molecular motions, meaning that if we have water molecules, they will be hindered more perpendicular to the fiber structure than along the fiber structure because of cell membranes. Think of all these microstructural constituents of an axon, the filaments, the myelin sheets. All these things, they cause your molecules to follow a pattern. This is kind of sketched out in more detail, right? So you see along the pathway, molecules would be less hindered, so they would be easier to propagate. And perpendicular to them, it's a bit more complicated for these molecules to spread out. So the cool thing is, well, if we have tissue, and tissue in the brain, like this fiber structure, causes your diffusion to be anisotropic, if we can measure the diffusion profile, then we could say something about the tissue properties. And in a way, it's a kind of an ill-posed problem, meaning that there's many different configurations of tissue that would result in the same diffusion properties if you were to make some assumptions about the diffusion profile. But we'll come back to that later today, and we can discuss this in more details. Okay, so the idea is diffusion also happens in the brain. And now with diffusion MRI, we're trying to estimate diffusion properties. Think of the diffusion coefficient that we saw in Einstein's equation. If we can capture that information, it will say something about the tissue. So for instance, if you're having a subject with pathology, well, we know that if there's pathology, might be something wrong with the brain. Well, what could go wrong with the brain? Well, you've got, some tissue degradation, right? So maybe the highly ordered fibrous structure breaks down, causing molecules to spread out maybe more isotropically, meaning that there's not even, imagine that you've got fibrous tissue, very coherent tissue, and it breaks down. Then it's not coherent anymore. So the anisotropic diffusion behavior that you had first is kind of damped, right? It becomes less anisotropic. These molecules, they will be able to spread out more quickly, across the boundaries, because these boundaries are breaking down, right? So diffusion can be a very sensitive marker of pathology. And so this is kind of the cool thing about diffusion imaging. Okay, you would be looking at a technique where the data that you acquire has macroscopic building blocks, like millimeter-sized voxels, but the process that underlies the acquisition is literally looking at molecules, ensembles of many, many molecules that are bombarding, that are probing the tissue. And so if at the microstructural level, like literally at, microstructure, like micrometer level, tissue is breaking down, because of water molecules being at the nano level, and there's many of them, and they're like feeling their environment, you have to think of it like that, then that process of feeling diffusion, if you can capture that and quantify, it says something about how the tissue is breaking down as well. So diffusion MRI is becoming very popular, especially in longitudinal designs, meaning following up people. So you scan them, and then, for instance, you monitor disease progression, or looking at the effect of therapy, like radiotherapy, or even chemotherapy, or other ways to look at, potentially, solving or mitigating the disease. I hope that kind of makes sense. And so, roughly speaking, you could say, well, with diffusion, you could think of free diffusion, the green line here. And obviously that would be the case if you would be looking at, for instance, the ventricles, right? There's no tissue in there. It's just a pot of water. Think of it like that. I think of the glass of water. Within the glass, molecules are free to move wherever they want until they hit the boundary. If you have tissue and it's hindered, and remember, with hindered diffusion, these molecules can still spread, but they're hindered, right? Then you'll get the red curve, meaning that your diffusion, your average square displacement of the particles, will have a lower, steepness compared to free diffusion. So they will be hindered, but not restricted. So if you're long enough, these molecules can go anywhere. With restricted diffusion, there will be a plateau. So this is kind of the blue line. You'll see at some point, it will not be able to continue anymore. All right. Let's move on. Well, I put this kind of denomination here on the restricted and hindered diffusion, because that's where our tissue is, right? In the free diffusion, we're not too, interested in the free diffusion at first, because we would be looking at a tissue where we have hindered and restricted diffusion. Very brief mentioning about the acquisition scheme. How it works is that if you think of your conventional T2 weighted imaging, you now add what we call diffusion gradients. And this is a part of the acquisition that allows us to look at the diffusion of these molecules. So remember with MRI, in the beginning, I told you, well, we would be looking at induced tissue magnetization effects, relaxation effects. And different tissue types have different relaxation properties. Well, if you add on top of that sequence, acquiring an image like that, another acquisition aspect to it, meaning that you add, you send in like a 90-degree RF pulse, meaning all these spins, they basically get flipped, if you want. So not the 90-degree pulse, the gradient, I mean. Then what basically happens is you'll induce a dephasing because of the gradient of the magnetic field that you apply. And then when you flip them with the 180 pulse, then they will start rephasing again when you apply this gradient. If your molecules did not move at all, like on the far right in green, you see all these molecules, there was no diffusion, then they will be rephasing, and then you'll get your echo, your signal. If there was diffusion, and this is kind of shown here, then all these molecules, because they were moving around along this diffusion gradient, if they were moving around, then because of the difference in the magnetic field, there will not be like a nice echo anymore. So they will not be aligned after the rephasing part, this transverse magnetization, and that will cause the signal to go down. Okay, I'm gonna try to explain this visually as well, and I'll start off with isotropic diffusion. Okay, so I'm showing you this animation now where I color encode the particles, with different colors along the orientation, the vertical orientation, which now assumes that the diffusion is in that orientation, so vertically. Okay, so what does it mean? Before I start the animation, I'll tell you what's going to happen. So in a moment, when I start the animation, I will let the molecules move around in an isotropic way. Right? We now know what that means. All these molecules, they spread in any direction with the same amount. Okay, the different colors, they reflect the different frequency that they have, because when you apply a gradient, in this case vertically, then the different colors along the vertical axis, going from blue to red, is basically reflecting the different precession speed. Okay, so they have a different Larmor frequency because you applied a diffusion gradient, and that gradient is a magnetic gradient. So the actual magnetic field will be smaller in the bottom of the animation, and it will be higher at the top of the animation, hence the different colors. Okay, and then in the dashed box on the right, you see a big arrow. This is what I call the magnetization. This is the signal, and it's a big arrow now. It's large. Let's start with that because it's large. Okay, so if I now start the animation, you'll see that because of the spread of all these molecules within the dashed box, you now have a lot of different colors, right? All these particles, they will have a different magnetization, a different precession speed. So, and if they're precessing differently, there will be dephasing, right? And so when there's a lot of diffusion going on, these molecules will not rephase after applying this 180 pulse. And so your signal will be gone. So I'll start the animation again. And you can see now on the right that the arrow is shrinking, right? So the longer you wait, the smaller the magnetization, because there will be dephasing going on because of the diffusion. This is isotropic diffusion in this case. If I now show anisotropic diffusion, but I'll keep the diffusion gradient again vertically, if I start the animation, and the diffusion itself will be horizontally. Okay, so what will happen is the molecules will be spreading around, but now anisotropically, where the horizontal orientation will be the main preferred orientation of spread of these particles. And so what happens now, as you can see, within this dashed box, you will still get the same colors, roughly. Okay? It might happen that there are some other molecules with a different color getting in there, so there will be a little bit of dephasing. So this magnetization will be a little bit smaller, but not a lot. You'll see that the signal will still be large because there's not a lot of dephasing going on because not a lot of molecules with different frequencies will be in that little box. Okay? And so the take-home message here is that with diffusion MRI, if you're acquiring data and the underlying tissue shows large amounts of diffusion in the same orientation of your diffusion gradient, so you'll be looking in a specific orientation with the gradient, if there's a lot of diffusion along that axis, then your signal goes down. Okay? And in the example that I show here, if there's anisotropic diffusion, but it's not aligned with the orientation in which we are probing our diffusion, then basically we'll still have a lot of signal. So again, if there's a lot of diffusion, the signal is low. If there's not a lot of diffusion, the signal will actually be high because the magnetization will be large. Okay, let's now show how this looks like in an actual acquisition. So now we show, what I'm showing you here are axial images. And on the left, you'll see a B0 image. And the three images on the right, these are what we call diffusion weighted images. And they have been acquired along three different, what we call diffusion synthesizing gradient directions. Okay, so you see something left-right, something up-down, and something front-to-back. Okay, this reference image is basically, think of it as a T2 weighted image. Everything bright in the image is basically reflecting a lot of water content. So you see, in the middle, very bright, the ventricles, the third ventricle. You see the, near the cortical regions, all the CSF there. All right. And then on the right, what you see there are diffusion weighted images. And let me zoom in on some specific regions. Well, if you focus on the ventricle areas where there's CSF, bright on the non-diffusion weighted image on the left. And then each of these diffusion weighted images, you see a dark signal. And this is basically reflecting, remember what I said earlier, if there's a lot of diffusion, the signal is low. Well, if we look at the ventricles, we've got free water molecules. They can spread around easily. They spread around quickly, right? Meaning there's no barrier. So these molecules, they just spread out. And so irrespective in which orientation you would be looking at in terms of diffusion, you've got the same amount of spread. There's no barriers. So this is isotropic diffusion, and it's large, meaning you've got low signal, and independent of which of these orientations of diffusion you will be looking at, the signal is the same. This is isotropic diffusion. And then I'm showing you these yellow areas. And if you know a bit about anatomy, the top one is indicating the genu of the corpus callosum, so part of the corpus callosum connecting left and right hemisphere in the front of the brain. Then there's the anterior limb of the internal capsule in the middle, and then the one at the bottom in the image is kind of reflecting part of the optic radiation. So what I've been mentioning is basically parts of the white matter structure. Okay, what can we learn from looking at these images? Well, let's focus on the top one, right? The genu of the corpus callosum. The left-right orientation of diffusion. So if you would be looking at, is there any diffusion going left-right? Well, it's a structure that connects left and right hemisphere. So, what I'm showing you here in this yellow ellipse is basically the area where pathways are going left-right. Well, if pathways are going left-right, you can imagine that the diffusion is also predominantly going left-right. It's not going up-down or front-back, it's going left-right. because that's how the pathways are oriented. And so if we look at the actual signal in those areas, two things that we can observe. First, in the left one of the diffusion weighted images, the signal is low. Well, again, a lot of diffusion means low signal. Okay, that's what we see. On the other orientations, going front, back, and up, down, we can see larger signals. And that kind of makes sense, right? Because perpendicular to the left-right orientation, meaning front, back, up, down, molecules will have a lot harder time to continue, right? Because of the barriers, the axonal fiber bundles. And so the signal will be high in those areas. So that's take-home message one. Diffusion along a pathway gives a low signal in the image, and diffusion perpendicular to main pathways gives a high signal. Okay? This is anisotropic diffusion, right? Because there's a clear preferred orientation in which molecules are moving around. And I will not go into details with the other structures, but similarly, you can see that the contrast is different across the different orientations with the other structures, right? So in the anterior limb of the internal capsule, you can clearly see that, in the up-down orientation, the signal is lowest. And this is what we expect, right? And if we look at the front-back orientation in the optic radiation, which we know, from LGN to the, cortical, visual cortex, it's going front to back. And that's also what we see here on the right. The signal is lowest. So by looking at the kind of joint orientation information and the contrast, we can already kind of see fiber structures popping out. But this is very visually, and we need to find a way to quantify this. Okay. Let's see. I have somebody raising their hand, I noticed. I don't know how to pronounce it. I'll give it my best shot. Shinichian Narges?
Yeah, correct. So it was a while ago, but I was just mentioning in the chat that there is a way to disable the lobby. And it was just for you. It was not a...
fantastic. You know what? I'll give it my 2 cents. So I don't have, because I've been doing this quite a lot. So give me 1 second. So open the calendar. Okay. Locate the meeting you want to disable in the lobby. Let's see. I'll look into this later. I'm not seeing it directly.
Yeah, just because the internet is unstable and everyone would be out at some moment and then coming back. That was just the reason.
Yeah, exactly. That's why I would be interested in doing this. Open the calendar. Okay, locate me. You want to disable the lobby. Click on up. Okay, let me see what I'm doing here. You know what? I'll do this in the break after my first lecture, and then I'll find some time to.
Yeah, no worries.
Yeah, okay. But thanks. This is much appreciated. Okay, I will continue then. Okay, so this is crucial to understand. Meaning, with diffusion MRI, we're acquiring a kind of a reference image. That's our B0 image or non-diffusion weighted image. It basically gives us an idea of, call it the water content in your brain. And then the diffusion weighted images, for each of these diffusion weighted images, you have to think of it as a specific orientation in which you are looking at, which describes the amount of diffusion along that orientation. That's what you're acquiring. And then you could think of it, if you have many diffusion weighted images with many different orientations, think of it like a flashlight with a, trying to look at your hand, your shade of the hand. So you're like looking at many different orientations, and you would be looking at the shade of your hand on the wall. And if you have many different projections along many different orientations, you can actually see it's a hand. But if you do it like this along your, in the view of the plane of your hand, then you only see a line. You basically see all your fingers, on top of each other. But if you have many orientations, you get a better profile of the object that you were looking at. Okay, so in practice nowadays, we would be acquiring more than 3 diffusion weighted images. We would be acquiring even 60 or even more orientations, diffusion gradients. And obviously, the kind of the law of conservation of misery, right? The more you want to know, the better data you want to have, the more time it will take to acquire all these data. And obviously, there's limits to it, right? So, lying in the scanner, maybe half an hour max, maybe an hour, really pushing this is the amount of time a person can actually lie in the scanner, with comfort. Let's call it that. All right. Okay. So now I'll take a kind of another step forward. You can kind of describe how the signal is decaying. And with decaying, I mean, remember when I said, like, if there's a lot of diffusion, the signal will be low. When you acquire an image, you need to apply a diffusion gradient orientation, but there's also another factor which is predefined. It's called the diffusion weighting factor, or diffusion, the B value. It's literally called the B value. And this B value, actually fun side story, B, why B? Well, B, this diffusion weighting factor, was proposed as a kind of condensed formulation of all these gradient properties, like, how big is the gradient and how long do you, activate this gradient, and what's the time difference or distance, if you want, the time between the onset of the 2 diffusion gradients, because you apply a gradient, then you do the 180 flip, and then you apply the gradient again. So all these kind of acquisition detail parameter settings, you can condense them in what we call the B value. And it was Denis Le Bihan, very well established, researcher. He's basically the grandfather of diffusion weighted imaging. I mean, diffusion NMR, like diffusion nuclear magnetic resonance imaging, that exists already from the 50s, 60s, something like that. But applying this technology into imaging, hence diffusion weighted imaging, that was, a lot longer. That came maybe 30 years afterwards. So it was only in the 1980s, like 1985, 86, that diffusion weighted imaging was actually proposed. And that was then proposed by Denis Le Bihan. And the B comes from his name. So he kind of admitted, like, I called it B value because of Bihan. It's a bit narcissistic, but I can see the fun of that. Anyway, so this B value is called, named after Denis Le Bihan. Anyways, so this B value says something about the acquisition. How long were the gradients activated? What's the distance, the time between them, and also their magnitude. And that's all kind of condensed into this B value. And if you look at the equation, it says the diffusion weighted signal is equal to the non-diffusion weighted signal times, and then e to the minus bd. Well, e to the minus bd is always smaller than 1, so you would be looking at the signal decay. That kind of makes sense, because remember, if you have more diffusion, the signal would be lower. Right? So the diffusion weighted signal should always be lower than the non-diffusion weighted signal. And then d is the diffusion coefficient. This is typically something that we would like to know what it is. And so if you acquire an image, a non-diffusion weighted image, and if you acquire a diffusion weighted image along a specific orientation, then given this equation and given a predefined B value, because all these settings are predefined about the gradients, like the time and magnitude, then there's only one unknown in this equation. Right? We measure S, we measure S0, we predefine B value, then we can estimate or compute what D is, the diffusion coefficient. All right, and so what I'm showing you here with the animation is that in practice we acquire multiple orientations along all these different gradient directions, not just along the circle, but think of it as a cross-section of a sphere. We're looking at many, many different orientations. All right, but obviously this is something to be aware of. Well, if you acquire a diffusion weighted image, and I'll just show you this example here. Add somebody to the lobby again. Okay, so if we were, okay, so how should I see? Okay, so when we acquire a diffusion weighted image, the contrast that we end up with will depend on the actual orientation of your head in the scanner. And let me show you the example. So on the left, we've got a non-diffusion weighted image. If I acquire a diffusion weighted image along a specific orientation, this is my contrast. Now, on the right, let's assume I rotated my head and then I acquired the image with the same diffusion gradient orientation. You'll notice that the contrast is different, which makes sense in a way, right? Because the orientation of the fiber structures in our brain, well, if you rotate your head a bit differently, think of it like this. Now my corpus callosum is nicely oriented left-right, but if I orient my head like this, then now it's in the reference frame of your scanner, it's not oriented left-right anymore. It's more like oblique to the back, right? If I take it to the extreme, I rotate 90 degrees. Well, in the scanner reference frame, my fiber structure is now oriented front-back. And so if you were to acquire the image, the diffusion that was left-right is now front-back. But if the gradient is staying the same, you'll get a different contrast. This is also crucial to understand, meaning your diffusion is rotation dependent. And this was a major issue to quantify diffusion, right? If you have a subject lying, let's call it a patient. Patient is in the scanner, and you want to estimate the diffusion coefficient because it says something about the tissue health. And then you do a follow-up, and you want to know, like, did my therapy work, or did it do anything? And you want to quantify this, and you would be computing the diffusion coefficient. But if the subject was slightly different in the scanner, then the diffusion coefficient would also change in that area, right? Because of the orientation dependence. So this was a big issue. And that was kind of solved by Peter Basser and co-workers. Actually, Denis Le Bihan was a co-author of the paper. I think he was a senior author on the paper. So, they both and the entire team came up with a way to quantify the diffusion in such a way that it was rotation invariant. So they came up with a framework, with a model, the diffusion tensor, as shown in the bottom, that could basically capture the covariance of your diffusion in such a way that no matter how you were oriented in the scanner, the actual diffusion coefficients that you would compute from this framework would be the same. And this was a major breakthrough. The ISMRM, basically the largest conference and society about MRI, they awarded Peter Basser the gold medal. Think of it as like a kind of a Nobel Prize in our MRI society. So that was a major contribution, and it opened the way to many new things. Just to give you an idea, when I started my career, my research, I started from the diffusion tensor framework. So I kind of owe my career to this development. But, having said that, it's kind of weird because I could even say like, I owe my career to the person that invented the computer because I use computers for my work. So anyway, point I want to make is it was a major leap in diffusion imaging and in MRI in a way. So yeah. Okay, now I'll give you a bit more detail about this diffusion tensor framework. As you can see, if you compare the diffusion weighted equation on the top, you see something like minus BD, and in the bottom you see minus B, and then gradient. The G is a gradient, the diffusion gradient orientation, and then transposed, and then times D, and D is basically a 3x3 matrix. In a fancy way we call it a tensor. Basically, in this case, it's called a second rank tensor, meaning there's rows and columns. So there's two indices to describe this mathematical object. And it's a symmetric one. And it's semi-definite positive, meaning that there's only positive values in there, meaning that, if you look at the diffusion coefficients are positive. They're not negative, right? So this gives us constraints in this framework, but I'll come back to that later. So anyway, it is written down like this in such a way that you can actually look at properties of this 3x3 matrix describing the covariates of your diffusion. So what's my amount of diffusion in the x direction given the y direction, stuff like that. Okay, before we continue, I'll do a quick intermezzo on what are eigenvalues and eigenvectors. You may have heard of this before, but I'll give a quick one-on-one on this, okay? Let's assume you've got this set of points, all these green dots. As you can see, there's a variance along the x-axis and along the y-axis. And they're also correlated, meaning if you look at these points, you can see that if x increases, y increases as well, kind of statistically, eyeballingly, right? There is what we call a covariance between the x and the y coordinates. Okay, what an eigenvalue decomposition does is it basically tries to transform your data in a new coordinate system. This new coordinate system is defined not with the x and the y coordinates as shown here, but with E1 and E2 in this case, or EX and EY, a new coordinate system in which the covariance is 0, okay, in which there's no correlation. Think of correlation, okay? So eyeballingly, it would be looking something like this. So if I were to place a new coordinate system along these points like this, you can now appreciate that along the E1 axis, if I were to increase or decrease this, my position at the E1 axis, well, it doesn't really increase or decrease the position at the E2 axis, right? So what I've basically shown here is that in my original coordinate system, XY, there was a covariance between the points. That was clear, right? As you can see here. Clearly, if X increases, Y increases. Like statistically, right? They're not on an exact line, but roughly you could say, there's a covariance. But in this new coordinate system with E1 and E2, there is no covariance. And this is kind of a, I'm gonna add somebody again to the meeting room. Okay, done. So as you can see here, there's no covariance, okay? There's no correlation. And so I'm going to skip the math, but what you see here basically is the mathematical details on how to compute this. Okay, so you need to set up what is called the characteristic equation, and then you can do all the math here. I'm going to skip the math, and I'll come back to basically my diffusion tensor. So in a nutshell, our diffusion tensor, like I said, is a 3x3 matrix. It's capturing the covariance, but if we were to decompose it into eigenvalues and eigenvectors, then as you can see here, the eigenvalues, they represent the diffusivities along the main axis right? So these E1s, E2s, E3s, think of it as your new coordinate system in which there's no covariance anymore. And the covariance is 0. And these are the zeros in this eigenvalue lambda matrix that we see here. Okay? The 3 eigenvectors are basically shown here in red, green, and blue. And typically, if you have anisotropic diffusion, there will be a major axis along which the diffusion is maximal. So we kind of sort the eigenvalues in magnitude as well. So lambda 1 will be larger than lambda 2, which will be larger than lambda 3. And so with this eigenvalue decomposition, our diffusion tensor is now rewritten as a kind of a linear combination of eigenvectors and eigenvalues. I hope this kind of makes sense. Okay, so again, take-home message. What Peter Basser developed was a framework which allowed us to look at diffusivities in a rotationally invariant way. And the trick to do that was to decompose this matrix, which describes the covariance in diffusion, and rewrite it in such a way that it becomes apparent that there's no covariance anymore. Because now, in each voxel, we have our own new little coordinate system. So what I'm showing you here, this ellipsoid, this is something you can compute for every voxel, for every data element. And the good thing is that if you were to rotate your head, well, it wouldn't matter because you would be computing your orientation for every voxel independently. Okay, so for every voxel, you have a coordinate system in which there's no covariance, and the magnitude of the diffusion will be the same irrespective of how you rotated your head. Okay. All right, moving on. So how does it actually look like? Well, if you look at one voxel, you get one ellipsoid. If you look at an entire data set, well, then every voxel has this little ellipsoidal element. Okay, so now I'm looking at the medial view of the right hemisphere. And, it looks a bit like a candy store, to be honest. Anyways, let's focus on a few details here. So first of all, let's look at the shape. Well, what I'm showing you here are all these little ellipsoids, and some of them are pointier than others. Well, those that are very pointy, they reflect high anisotropy, meaning there's a clear structural, coherent organization underlying those data. And actually, in regions where there was CSF or gray matter, I actually removed those from the visualization. And then the color, you may say, like, oh, all this, green and red and blue, what does it mean? Well, there's an elegant way to visualize the orientation of these ellipsoids by color encoding them in an RGB color encoding scheme, where red, green, and blue basically represent the absolute value of the orthonormal vector associated with the dominant diffusion axis. So remember when I said like these ellipsoids, you can geometrically look at them as having these 3 axes, the 3 eigenvectors. And I said that these eigenvectors, these axes of these ellipsoids, they reflect, they are corresponding to the eigenvalues, and they're sorted, meaning that the first eigenvalue is associated with the first eigenvector. And if there's a lot of diffusion, this lambda 1, the first eigenvector, will be large. And if it's anisotropic, it will be oriented along a specific axis. Okay? And so everything which is pointing in the left-right orientation is given a red color. Everything going front to back is given the green color, and everything going up-down is given a blue color. And this is because the orientations would be, 1, 0, 0, 0, 1, 0, and 0, 0, 1. These are the normal vectors in those orientations. Okay? And any color in between, like, orangey or cyan or purple, let's stick to purple. Well, purple, how do you get that color? Well, it's a mixture between red and blue, right? Well, red is pointing left, right. Blue is pointing up, down. Well, if it's pointing not up, down, not left, right, but in between, it will have a color of something like, 0.50, 0.5, right? And so you'll get a purple color. So it gives us a natural way to kind of showcase the orientation. Let's see, I see a chat. Okay. I do not have a voice. Okay. Luckily, I've got the voice because I'll be talking. All right. So continue. So this is the idea. So we now have all these ellipsoids. At every location, we have at every location we have this ellipsoid, and this ellipsoid has an orientation and a shape, and both are important to understand. The diffusion that underlies the tissue. But obviously in practice, we don't show these ellipsoidal maps. All these ellipsoids, that's not convenient, right? It would take too much time for a doctor to really understand and look at all the little details. It's kind of cumbersome. So it would be more convenient to have maps, just images. And one elegant way to create a map is to look at the shape of this ellipsoid. And you can quantify this anisotropy with a measure called fractional anisotropy. And it's basically a kind of normalized standard deviation of your diffusivities along the different axes, right? If there's a lot of difference in magnitude of diffusion along different axes, we'll call it highly anisotropic. Very pointy, cigar-shaped ellipsoid. And we'll give it a value of 1. And the more it looks like a sphere, the lower the value, and we'll give it a 0 if it's completely isotropic, meaning there's no preferred orientation of diffusion. And so if you look at that, if you were to map that out, it would look like this. Everything in the white matter gives, so all these bright regions, they're basically reflecting white matter regions, okay? Because in the white matter, there's a clear structural organization with a preference in which these molecules are able to proceed, right? So this is what we call an FA map, fractional anisotropy map. So the brighter the image, the higher structural coherence that underlie this anisotropic diffusion. Okay. Well, this is kind of a summary on how to compute it. It looks maybe scary, but it's just simple algebra based on the eigenvalues. So the lambdas here in the formula, they represent the diffusivities along these axes of the ellipsoid. You can also see there's kind of an average lambda, and that basically gives you this basically the average of the 3 eigenvalues. All right, and there's many other properties that you can look at. Another one, which is very popular, is basically the amount of diffusion. Okay, so you've got the size of these ellipsoids. So if you have a big ellipsoid, it means that the spread of these molecules is quick, like they move and they can quickly go far away. And obviously in the ventricles and CSF areas, there's no barriers, so the diffusivity will be high. And if it's low, think of hindered diffusion or even restricted diffusion. These molecules, they cannot spread further or have difficulties to continue because of tissue, and there will be a low diffusion amount. All right. Then there's even more types of diffusion. Well, we can split up the amount of diffusion in the component along the pathway, along the first eigenvector, or perpendicular to the first eigenvector. So if you focus, for instance, on the genu again, so the front part of the corpus callosum, the longitudinal diffusivity will be high because there will be a lot of diffusion along the pathway. By contrast, on the right image, the transverse diffusivity or radial or perpendicular diffusion, these are all kind of synonyms to each other. If you look at the amount of diffusion there, it will be lower, right? The signal will be lower in that image because of barriers. These molecules, they cannot quickly progress against the orientation of the pathways. And again, every diffusivity, as we call them, like mean diffusivity, or also mentioned or referred to as apparent diffusivity coefficient or diffusion coefficient, the ADC, that's your average eigenvalue. The longitudinal diffusivity is basically the diffusivity along the first eigenvector, which is lambda 1. And transverse diffusivity is perpendicular diffusivity. And that's defined as the average of the second and the third eigenvalue. Something I want you to remember here is that fractional anisotropy and mean diffusivity are independent of each other. And I'm showing you with this example, from top to bottom in each row, on the middle, left, and right, from top to bottom, fractional anisotropy goes down. Okay, so on the top you see a very pointy ellipsoid, and in every of these three columns, you see at the bottom that the shape has become a sphere. So we go from very anisotropic diffusion to isotropic diffusion. Okay? That the difference between the three columns is basically in the left one, you can see also that the size of the ellipsoid is decreasing. So the mean diffusivity decreases. In the middle part, the actual size of the ellipsoid will be the same. So the mean diffusivity stays the same. And on the right, what I've actually shown is that the ellipsoids are also, kind of growing in volume. And that kind of reflects an example where the mean diffusivity would actually increase. So what I've shown you here is that irrespective of what the fractional anisotropy does, mean diffusivity, can still increase, stay the same, or decrease. So they're independent of each other. All right, and moving on. So we now have these kind of ellipsoidal maps, and I told you, well, it's not convenient to look at these ellipsoids. We've focused in a few slides ago about the fractional anisotropy map. So that's a very popular map that kind of indicates the shape, the amount of anisotropy in the diffusion profile. I've talked about the color, and obviously you can see these ellipsoids here in this axial slice, different colors with the convention, again, red, left, right, front, back, green, up, down, blue. But we don't show a map like this. We show maps like these. And now you see and colors and brightness. The brightness that you see is still the fractional anisotropy map, but now the colors are basically the same as the orientations that I show you here, but now it's visually more appealing because of the continuity in the map. You don't look at these discrete glyphs, these little objects. Now you look at a continuous profile. And mathematically, remember, I told you that the color information can be easily obtained by taking the absolute value of the first eigenvector. So this is in short FE, first eigenvector, the E1 if you want. And it's an orthonormal vector. So the norm is 1. So if you look at the left image, although it's very colorful, the brightness is the same everywhere, right? It's an orthonormal vector. So RGB, if you look at the norm, it's all 1. On the right, you see a fractional anisotropy map, which basically has the brightness. And the cool thing, obviously, is that if you look at this map, like the previous slide, you see the colors and the brightness. Well, it's basically a multiplication of the absolute value of the gradient of the eigenvector components x, y, z, and multiplied it with the fractional anisotropy. And then if you overlay it, you'll get the map that we're all used to looking at. I mean, at least I am for 20 years. So this is what we call a direction encoded color map, a DEC map, or a color encoded FA map. All right. And so the cool thing is now, well, with a T1 weighted image, we can get very high resolution. We get a nice kind of interface between white matter, gray matter, high resolution. But within the white matter, obviously, as shown in this image, if I focus on this little area in the middle, Or are we looking at pathways going up, down, left, right, front, back? We don't really know. But now, with our new technique, diffusion tensor imaging, we can actually combine best of both worlds, right? We can now realign the images, like register the images from, diffusion space to T1 space. We can maintain the high resolution, nice contrast between white matter and gray matter with the T1. But then within the white matter, we can then use that color information that gives us an idea about the orientation of the underlying tissue. Okay? And what that means is that within the white matter, we can become a lot more specific. And I'm showing you this example here. This is actually, I can tell this. This is Russ Poldrack, his brain. And Russ Poldrack is a famous Stanford professor. He's a psychologist or cognitive neuroscience. And let's call him a neuroscientist, but a very smart guy. And he basically scanned his brain for an entire year, like every week. And he wanted to investigate his connectome, his brain. And at some point, he asked me to help out and analyze the diffusion data of his brain. And he sent me his brain, and I saw something abnormal. And I'll already give you a clue here. It's in this yellow rectangle. And on the T1, you can't see anything abnormal, right? And I shouldn't necessarily call it abnormal, but something rare, because apparently it's not abnormal. It's just not seen often enough. So it's about frequency, not about being normal or abnormal. Okay, something I learned. So if we focus on that area on the diffusion data, well, you can clearly see something weird. Well, again, something unconventional, because focusing on that area, it's part of the corpus callosum. And remember, corpus callosum, it's a structure that connects left and right hemispheres. So it's oriented left-right. And so if we look at the diffusion profiles and at the ellipsoids, you would expect the color to be red. And as you can see, in most of this area, you see a reddish color. But you also see this green patch, a region where the diffusion appears to be oriented front-back. Let's focus on the sagittal view. You can also see on a sagittal view that the orientation is front-back. And even if you take a closer look, you could also see that on top of the corpus callosum, there's also a structure going front-back. Remember, this is mid-sagittal. It's not more lateral, so it's not. These are not the cingulum bundles on top of the corpus callosum that you see here in green, but it also literally goes through the corpus callosum, as shown with the right arrow. Okay, so that was an interesting observation. I'll come back to that later, but one of the thoughts I had was like, oh, is this an artifact in the data? Was there some issue? Well, this is very high quality data, and I'll come back to that later, showcasing that it's not an artifact. So again, this is just a rare configuration. You can generically call it a hyperplasticity of brain pathways or unconventional configuration of the brain architecture. But it's very interesting, at least to me. Anyways, okay, so let's continue here. And so, well, I just showed this animation kind of because I liked it. So what I basically did here is you can also look at gray matter, because we've mostly been focusing on white matter, right? Because there's the fiber pathways, but obviously gray matter also has a structure, the laminar structure, the different layers, and then on many stainings or drawings or images, histology, sometimes we think of the gray matter as kind of a less organized structure, but there's also a lot of organization there, but it's very thin compared to the white matter bundles, right? So some regions, maybe 1-2 millimeters. Well, that's kind of the resolution at which we are acquiring our data. And so on typical maps with a resolution of about 2 millimeter isotropic voxel size, it's difficult to capture the organization in the gray matter in an let's say in a reliable way. But nowadays, we can scan with a high resolution. There's something called a connectome scanner, which allows you to acquire data with a high resolution. But other scanners, clinical scanners nowadays as well. You've got multi-band and all these acceleration techniques to speed up the acquisition, which you can then trade in higher resolution. I mean, trade is the name of the game in MRI, right? If you want to acquire quicker, then you unfortunately need to kind of get bigger voxel sizes or stuff like that. So you always need to trade off properties of an image. Well, nowadays, high resolution cortical information can be obtained, and you can investigate this. And that's what I'm showing here. What I'm basically showing here is that the cortical surface, the pial surface, and on top of that, I'm showing you the local organization of fiber tissue. Again, focusing on the dominant orientation. So that was kind of a cool try to see how does it look? And it's kind of showing you, in a way, properties that you expect, right? Everything going left, right is in red, up, down in blue, front, back in green. So there is a kind of preference in which how pathways enter the cortex, which is typically perpendicular. So perpendicular to the cortex, you see the orientation of the underlying dominant orientation on average. And this is not perfect, right? All right, moving on. Obviously, NeuroTRACT, tracts, tractography, fiber pathways. Well, we haven't seen any yet, right? But we've always been saying that with diffusion, you can probe this architecture. Well, if you look at, in this case, the splenium of the corpus callosum area, well, we see all these ellipsoids, and they're all pointing to each other, and our brain is already connecting all these discrete elements, right? Mm-hmm. If I were to reduce the ellipsoids to the dominant orientation, it's not hard to imagine that you can actually connect all these little discrete elements. And in a way, it's the same like looking at this cartoon, right? If I ask my kids to connect the little discrete elements here, they can do this. They will draw this line. And we're doing exactly the same with fiber tractography, right? We have our discrete elements of orientation in the data, and then we have starting points, seed points as we call them, from which you start connecting these little lines. So you take a little step, and then you look in 3D, right? I'm showing you this kind of 2D-ish version, but each time you basically take a next step, and then you can reconstruct kind of the pathway that runs through the data. Think of it like streamlines, like in a stream, like a water, like in a river, right? You can follow the line of the water moving in the river, right? So we're doing something similar. We're just following the orientations, and we take a step, and it looks continuous now, right? Because in 3D, you take a little step, you look like, where do I need to go there now? Let's follow this dominant orientation of diffusion. And each time you take a little step. And when do you stop? Well, you stop, for instance, when at that location, the fractional anisotropy is low. So what does it mean? It means that at that region, the assumption is that at that region, if the FA value is low, if the anisotropy is low, it basically reflects that there's no clear preference in orientation of your diffusion. Again, in turn, reflecting maybe that you're entering a region of CSF, right? If you enter a cortical region where you end up in the gray matter or the white matter where there's no clear preferred orientation, think of a sphere. If I ask you what's the preferred orientation of a sphere, well, it could be any orientation. And so if this orientation is then at a specific angle larger than some threshold, you can stop tractography as well. You can stop this propagation of these lines. Okay. So yeah, this is what we call fiber tractography, kind of virtual reconstruction of fiber pathways. And Here's my 50 cents of nerdiness. All right. I don't know if you can hear the music, but, well, let me stop the music for a second. So it is like this Star Trek adventure in a way, right? So a starting point in the data is basically moving and finding areas and then following the dominant orientation of these ellipsoids. And then you get something like this animation that I made, 20 plus years ago. So it's a bit old-fashioned, but, it just makes the point again, right? So we're following the dominant orientation and we're moving across the data. And in practice, we don't just sample one point. We don't have one starting point in the data. We start everywhere in the brain. So we got multiple starting points, multiple seed points, as we call them. And then you end up with something like this, right? This kind of spaghetti-like representation of pathways in the brain. And keep in mind, these are not direct representations of pathways, right? I once had one junior neuroradiologist, and he came up to me and he said, "Oh, Alex, I didn't know axons were that thick." Okay, so obviously the thickness of these little tubes that I'm showing you is not reflecting in any way thickness of pathways. It's just a way to convey the architectural configuration with shadings, and you get an idea of how these pathways are represented in the brain. Okay, it's just a visual representation. But the cool thing is, we can now start doing something like virtual dissection, because these pathways, they connect different brain regions. Well, if we have prior knowledge about what regions we are looking into, what regions we like to see connected, like what are the pathways connecting the spinal cord and the cortex? Well, boom, you see these purple ones. You see these corticospinal pathways, these projection pathways going up, down. And with prior knowledge, placing regions of interest in the brain at specific locations, we can tease out pathways of interest. Okay, and this is in a way fantastic, right? We've got an in vivo dissection approach, and we can now quantify properties of these structures. We cannot just visualize them. We can now also look at properties, for instance, the mean diffusivity or fractional anisotropy, or we can quantify their approximate volumes, like, does size matter, in fiber tractography analysis. We can look into those things. But, and this is a big, warning, is that, Ceci pas une pipe, we all know the art, but the same holds for fiber tractography. Some people also find it a bit artistic, right? They say like, oh, nice tracts. Well, you have to be careful about calling them tracts. It might be more wise to call them tracks, like CKS instead of CTS, because these are trajectories. These are fiber pathways as reconstructed with fiber tractography, which has parameter settings, which is based on the diffusion tensor model, and this model has assumptions, and I'll come back to that later. And so it's an indirect way of reconstructing these fiber pathways. Okay, so although it looks like an uncinate fasciculus, it's not a direct representation of the uncinate fasciculus. And again, why do we give thickness to these pathways? Well, this is just an example. On the left, it's difficult to say, is it looking from the top or the bottom? And on the right, it's clear that we're looking from the bottom, right? There's shading, you get a better, it conveys the architectural configuration more clearly. And I'll put it to the test, right? I'm showing you two results of fiber tractography of the uncinate fasciculus. One is the left side and one is the right side. Well, without shading, you can't really disambiguate both structures. But if I show it like this, well, we know that the orbitofrontal cortex is connected to the temporal pole through this structure, and the temporal pole is lower than the orbitofrontal part. So now we know, this image on the right is actually the left uncinate fasciculus, And the image on the left is actually the right part in the brain, in the right part of the brain. Okay? Let's see. I noticed a lot of chats. Let's see if I can quickly go through them. So hold on. Will there be a break soon? Yes, yes, we're almost there. Let me just double check here. Well, maybe it's a good time to have a quick break here, but I'll come back to that in a moment. Let me just read here. The lunch break will be at 1:30. Tehran time. So what time is that in Dutch time? Well, anyway, let's see that in a moment. Okay, blah, blah. Okay, there's a question. Can low FA refer to a region where multiple tracts meet each other? Exactly. That's a very good point, and we'll discuss it at length in the next lectures as well. So in a nutshell, when multiple fiber pathways meet each other, at that location, you may argue that it's not a real anisotropic region anymore. Okay? Because you've got many orientations now where all these different pathways meet. So it becomes isotropic then. And so the FA goes down. So, but we'll come back to that later. Okay, 11 o'clock my time, that's in an hour and 45 minutes. Okay. So Mohammed, can we differentiate between left or right? Well, if you're referring to the Wilson fasciculus, by just looking at it, I'm showing you now, again, it requires a bit of anatomical knowledge. But if you look at the left image, then the lower part is the part that connects the temporal region, and I can actually show it this image again. If you look at this animation, this is the lower part. This is the temporal region, and then this top part. This is the. I don't know if you can actually see my mouse cursor, but I'm now pointing at things. I hope you can see it. Going to this image without shading, you can't see, but with the shading, you can actually see the configuration more clearly. I mean, it was just to emphasize that we use this shading and the tubes to get a better idea of how these pathways are running, but they're not reflecting a genuine thickness. That's something to keep in mind. Okay, let's see. I think we're almost there, but let me just double check because I don't want to. Oh, no, we're almost there. We're almost there. So I would suggest we keep on for 5 minutes and then we can have a break. I hope this is fine. All right. So let's continue here. Oh. So let's continue. Okay, validation is always a big concern because when you come up with a new technology and you claim to be able to reconstruct pathways, in vivo, that's gonna cause a big frown. Like, wow, can you really do that? Well, what I'm showing you with this image, on the left is the histology, on the right is the in vivo. Well, this part of the projection pathways, of the pyramidal pathways, well, if it looks like a duck, quacks like a duck, flies like a duck, and even tastes like a duck, it's probably a duck, right? And so, at least from a highway point of view, we're doing something right. But we'll come back to the limitations and all the issues related to validation later on. But the point I want to make here is that, we've got new technology, and it seems to reconstruct pathways with anatomical accuracy related to what we think that the pathways are located and how they are, configured in the brain. But I'll come back to that at length later. All right, a few application examples before we end. Well, here's an example. Well, this is not a human brain. This is actually a starling brain, so a songbird. And here there was a preclinical research application. These were biologists, and they were interested in looking into this songbird's brain, especially the auditory system, right? And in particularly, they would be looking at 9 male starlings, and they would be looking at their brain in spring, because in spring, obviously, we know what they do in spring. They're all horny, they want to mate, so they whistle a lot to attract females, right? And so they do their thing, and then in summer, they're all done, smoking a cigarette, whatever. They're doing their thing, and they don't whistle a lot anymore in summer. So obviously, the equivalent would be like, talking a lot or singing a lot, with humans in spring and not doing anything in summer. But their brains are very plastic. This is something which is well known. And so the question here was like, can we see any differences between spring and summer in terms of their brain connections and how the diffusion properties would change? And, a long story short, yes, there were many brain regions that showed a significant difference between spring and, let's see, I got another request here to enter the meeting room. Okay. So there were many differences in fractional anisotropy at various locations throughout the brain between spring and summer. And obviously all these biologists, they were very happy, and apparently these song nuclei in the brain, they corresponded to the regions where the differences were biggest, right? So that was cool. And actually, if you do tractography, well, on average, you can see that there seems to be bigger connectivity in spring compared to summer. So that kind of reinforced the belief that there was a large neuroplasticity going on, and that diffusion MRI was able to capture this change between spring and summer. And since then, many studies have been showcasing the use of diffusion MRI and DTI in particular to capture properties of different pathways. And this is an example where, according, if you age, growing up, developing your brain, you can actually see properties of diffusivity changing, and that these changes are different for different structures in the brain. So that's pretty cool. Obviously, in a clinical arena, and this is where a lot of interest is nowadays, is looking at how diffusivity and diffusion properties in general change with respect to therapies. And in this case, in this study, it was shown that diffusion properties were actually correlated with cognitive functioning, and that these changes, were due to chemotherapy, and so in this case, these were breast cancer patients, and they received chemo, and they were complaining of cognitive malfunctioning, and there was an association between the amount of cognitive problems and diffusivity estimates. So in this case, I think, the higher the cognitive issues, the more complaints, the lower the fractional anisotropy. Okay. And another example, and this is an important one that has a lot of potential, is looking at neurosurgical planning. Obviously, if you have a tumor and it needs to be resected, you want to minimize collateral damage. And by looking at how pathways, the eloquent pathways, are located around the tumor, you can take that into account when planning the location in which to do the resection. Are you going to remove the tumor from the top, from the left, from the front? You want to minimize collateral damage, and having information about the pathways is kind of convenient. Also, interpretation of fiber architecture. This is a normal subject. On the right, well, Mrs. corpus callosum. Well, obviously you don't need diffusion to see whether somebody has a corpus callosum or not. You can see this on the T1, but instead of the corpus callosum, this person had what is called Probst bundles. So these are kind of, well, you can call it association pathways that kind of replaced the corpus callosum. Anyway, it's quite interesting to look into this. But from a cohort-based type of research, any any pathology that you could think of has been used to, with diffusion MRI to investigate. All the ways from epilepsy, Alzheimer's, all the way to dyslexia. All right, and keep in mind some of the valid examples that you can think of is like, is there a difference in the microstructural organization of white matter fiber bundle X between healthy controls, subjects with pathology? Or can the severity of a disease condition X be reflected by the microstructural organization of fiber bundle Y? Another one, in a longitudinal follow-up design, what is the differential effect of medication X in tract Y for pathology Z on the microstructural organization? Notice in each of these three questions, I use the terminology microstructural organization. And this should always be considered in terms of diffusion metrics, right? This is our ammunition. This is the tool that we have to look at disease progression. For instance, looking at specific questions, right? So what we cannot do, and this is an invalid example, is, well, you acquire a data set and then you just ask, does this subject have pathology Y? It's going to be difficult. You cannot be specific to a disease with this technique. And to finalize, well, we've been focusing on the brain. Well, we can look at diffusion MRI in any tissue where you have structural coherence. Obviously, you could look at nerves in the peripheral systems, like the sacral, lumbar plexus, look at those. But, and even ex vivo, you can look at that. You can even see on the right bottom, we see even like the nerve roots entering the spinal cord, right? So this was an example where, you can already picture this on CSI Miami or something like that, right? What's the cause of that? Oh, we don't know. Let's do a diffusion tensor imaging. And then we can look at the fiber architecture, and then we can know why this person died. Oh, it was an overdose or whatever. Doesn't really matter. But the point is, we've got these new techniques, and they're now emerging to other fields, like in forensics. So this is pretty cool. Here's another one. What is this? Well, it's definitely not a brain. Well, this is actually part of the kidney. Right? This is a medulla of the kidney. And because the kidney also has highly organized structure in there, these kind of pyramids, and it filters the blood to get your urine anyway. And so you basically can now look at these structures and how kidney deficiencies could be investigated. So anything in terms of strategies looking into disease progress or strategies for therapies can now be quantified with diffusion properties in the kidney as well. So that's good news. And if you're thinking outside the box, because of all these cool neuroimaging things, you can also just 3D print them. You can even make jewelry out of these 3D prints. So you can already imagine, like, hey, honey, will you wear my uncinate fasciculus tonight as an earring or something like that? So yeah, lots of potential there. And I think with that, please don't panic. Okay, so this has been the first lecture. So apologies for taking quite long, but also because of hiccups and all these things. So we've been chatting for 2.5 hours. I can imagine some of you need a toilet break. I might need one too, and a cup of coffee. But before we go, any questions? Well, thanks for the thumbs up. So feel free to just, what would be easiest is obviously, just unmute yourself and start talking. Maybe with your camera on. It's always nice to see a face. Or, if you feel uncomfortable, just chat your question. That's also an option, and then I can just answer. So I can do that as well. Let's see. So any questions, feel free to chat or just unmute yourself put your camera on. I think somebody is talking, but it's very, very quiet. I can't really hear. Again, I think I hear somebody, but I can hardly hear the person. So either the microphone is not working. Maybe somebody else can quickly say something so I know it's not me.
I don't think it's you.
Yeah, okay. This was a very clear voice. So then I suggest the person that wants to say something chats it. Let's see. Yeah, I see something chat. Okay. Is there a reference I can use to read more on the subject? Sure. Well, let's. Okay, I'll be very self-serving here. Okay, what I'm gonna do is I'm gonna quickly chat a link to my papers, and obviously, you don't need to look at my papers per se, but if you go to my Google Scholar profile, a lot of these papers are accessible through that link. And what I suggest you do is go to those papers that are like review papers. So, okay, let me chat a concrete example here. So here's a link to a review paper I wrote, it's actually 10 years ago, I think. I don't know, let's see, where's the date? Yeah, it's exactly 10 years ago. So that would be a good start. And obviously, I always say if you can't find it, Google it, right? So that's also an option. But also, let's see. Let's go to a more recent one. And again, I know this is self-serving, but these are obviously the first that I think of that come to mind. Here's one on tractography. So that's a recent one from last year, something like that. And then obviously look at the references in those papers, right? All right. So I see more people with hands being raised. So feel free to either unmute yourself or type into the chat your questions. I can also imagine that some of you are like, oh, I need to go to the toilet. Please stop. We can do that too, right? And then we can continue with questions after the little break. Shall we do that then? "15 minutes is fine. I can get a cup of coffee, do a little toilet break, and then in 15 minutes we'll be back online. But I don't know how it's going to work. So maybe just leave your, let's keep this meeting platform open. So I'm not going to, get out or something, right? I'm just going to mute myself and turn off the camera, but stick in this room, right? Don't move away, because I might not have found out how to admit people to my lobby automatically yet. So stick to the meeting area, okay? Don't go anywhere. All right. I'll see you guys in 15 minutes then.